But I hope you guys are doing well nonetheless. Almost at the end of the semester, which means we almost have spring break. We got spring break coming up next week, conveniently just in time for the end of the semester. So hopefully can use that week to get some rest and catch up on things. But just so you guys know, got homework assignment due this week. I changed the due date on that. It's not due tonight since we're going to cover some stuff which is on that homework assignment. You're going to have one more homework assignment that's going to be due after the break. So we've got two more homework assignments. One is due before the break. One will be due after spring break in the last week of class. And then we've got our third exam, which is scheduled during finals week. So our final was determined by the official final schedule, which means we're on Monday, May 10th. So our third exam will be Monday, May 10th. It's scheduled from 2 to 4 p.m. Just know that the exam is not a full comprehensive final. It's going to just focus on the content that we've done since the last exam. So that will be estimators, confidence intervals that we've been talking about, and we'll talk about hypothesis tests some more after today. So 2 homework assignments and an exam, and then you guys have summer break. Great. So any questions about things before we get started for today? Just trying to share my screen. Great. Okay, I'm gonna share a couple of documents in the chat. So we're gonna start working with an R markdown file. It's in Canvas too, so you might be able to track it down, but I'll put it in the chat. The file is called confidence interval practice. That's over there. And if you want to follow along with the worksheets, I'll put those in the chat as well. So we'll finish up working with means on confidence intervals, and then we'll talk about how we do confidence intervals for proportions. So the plan today is to finish up worksheet 14, cover worksheet 15, and that's going to involve doing some stuff in R, and that's what the R markdown file is for. Okay. So where we left things last time is we did some examples where we were doing confidence interval for a single mean when we knew what the variance of the population was. So that was, doing some examples back here with the Komodo dragon, where we assumed that we knew what the variance of the population is. But like I said, when we're doing this, we usually don't know what the population mean is. So it's usually the case that we don't know what the population variance is either. And so in those cases, we replace the standard deviation in the formula for the standard error. We're going to approximate the standard error using the standard deviation from the sample instead of the population. And rather than use a normal distribution, we use a t-distribution. And depending on our sample size, that's going to determine how many degrees of freedom we have in our t-distribution. And so this is where we pretty much let things off last time. We actually didn't construct a confidence interval for the next question. I think we started talking about it. So the idea here would be, let's say we want to come up with, in this case, 99% confidence interval for the mean weight of all babies that were born in North Carolina in 2004. Let's see how we can set up a confidence interval for that. And again, we did start to talk about this a little bit last time, but yeah, we have like almost a week between classes. So let's kind of just catch us up. So this is the data set, which is in the library resample data. And from that, we can calculate how many values, how many observations were in the data set, what the mean of that sample is, and we can calculate the standard deviation of that sample, and then we can try and calculate what the value of t alpha over 2 is. And so I'll kind of do it on paper, and then we can compare it with what happens in R. So here we're working with this data set, NC births 2004. And we want to come up with what is the average Okay, so maybe we want to use that data to come up with the mean birth weight of all newborns that were in North Carolina in 2004. And here's our confidence interval. And so we're going to find upper and lower bounds for this interval. And then we're going to use R to calculate all these things. So I'm not going to do the calculations here. Just want to make sure we're comfortable with the ingredients. So this is going to be our sample mean. So this would be like our point estimate. Meaning if I were going to estimate this population parameter with a single value, that would be my best guess. But we should build in some error due to the sampling. So S, this is the standard deviation of the sample. Right? N would be the sample size. And so between these two things, we can get an estimate for the standard error. And again, right, we just plug in the sample standard deviation rather than the population standard deviation. But because of that substitution, there is a little bit more error. So we use a t-distribution. Right, the degrees of freedom are going to be n minus 1 in this case. So if we have 1,009 observations, we're going to have 1,008 degrees of freedom. In this case, we wanted to find the 99% confidence interval. Oops. So we can think about this t-distribution, which looks very much like a normal distribution. And we want to find what this value over here is, and it's got a counterpart over here. So these are going to be the values that we adjust based on the confidence level. And in this case, we would say, okay, we're going to use R to calculate this. I can find this by figuring out what's all the area to the left of that value. So in this case, we take that middle 99% and half of the missing stuff in the tails to also include the stuff in the left tail. So the first argument in the QT function would be how much area do we want to the left, and then the second entry would be the degrees of freedom. So then our margin of error would be this multiple times the standard error. So that's what this stuff over here is. Once I calculate the margin of error, I add that to my point estimate to get the upper limit, and I subtract it from my point estimate to get the lower limit. So we could also think about this as x bar plus the margin of error, x bar minus the margin of error. And I think that's a catch up to where we left things last time. We actually didn't do any of these calculations yet. So any questions about the plan of attack? So we're going to use R to calculate these since we've got like over 1,000 values. Okay, then I'm going to move into this file, which is the R Markdown file that I added to the chat before. So rather than mark up the PDF, I'm going to open up RStudio. And here is this confidence interval file, our markdown file. Okay, and I don't need this stuff over here, so we can get rid of that. Okay, is that, can you guys see the screen? I guess you can see your screen if you've got that open. Okay, so yeah, so here's the same question in there. So we want to construct a 99% confidence interval. So for the point estimate, I am going to first break off the data that I need. So I'm going to go into North Carolina births, 2004, and just create a data vector that I'm going to call sample that just has the weights in them. I don't need all of the other variables that are in the data set, for example. So that's going to give me a vector of the weights. And now I'll calculate my point estimate, which is going to be the sample mean, by taking the mean of my sample. And while I'm here, I might as well double check how many things are in my sample by using the length vector, the length command. And here, since we all have the same sample, you can check this. You're going to need to load the resample data library, first of all, to use NC births. And then here, I am getting the 1,009 observations and this 3,448.26. That would be my point estimate. That's the mean of my sample. But of course, if we picked another sample, we would get a slightly different mean. So let's kind of build some error into that estimate to reflect that. Any questions about that so far? Okay, so then let's kind of get into how we can then build the margin of error. So the margin of error depends on the confidence level. So for this, notice here, we're going to use a t-distribution since we do not know the population variance. Our sample had size 1,009 observations. So our t-distribution will have degrees of freedom equal to 1,009 minus 1, or 1,008. So we usually shorthand the degrees of freedom with df. Sometimes people use a v for the degrees of freedom. If we knew the variance of the population, then we would use a normal distribution. So I'm going to call this value t star. This is like the t alpha over 2. I'm just not going to type alpha over 2. And so for this, we're going to use the quantile t-distribution function, right? Because it's a 99% confidence interval, we're going to put this here, right? Because that's the middle 99% plus the 0.005 that was in the far left tail. And for my degrees of freedom, since I already calculated what n was, I can input that into the formula, right? Or I could just enter 1008. And I want to see what this is. So I'm getting 2.58. So please let me know if you have any questions about what I did in R, or if R is giving you any trouble. Okay, so next up, standard error. And here, this standard error, right, we're going to get by taking the standard deviation of our sample that I saved in this vector called sample. And we're going to divide that by the square root of the sample size, which I stored in n. And again, if you call things different names, just be sure you're being consistent with that. But again, because we are all working with the same sample, you can be checking that we're all getting the same answers here. So my estimate for the standard error when we use the standard deviation of the sample is about 15. So then the margin of error, I'll call that the mean. That would just be the value that we got for t star times the estimate that we got for the standard error. I'm breaking this down into different steps. You clearly could do a lot of these calculations all in one line if you want to. So margin of error here we can see is about 40 grams. And so now we're ready to put all of this together. We've got our margin of error and we've got our point estimate. So I can say my lower cutoff here would be my x bar minus the margin of error. My upper cutoff would be x bar plus the margin of error, and that would be it. And so if you want to check these out, I'm getting lower cutoff of 3,408-ish grams up to 3,488 grams about. So these are being measured in grams. Okay, any questions about that process? So it's kind of like find the point estimate, find the margin of error, and those are the two bits that you need, right? And I think that the tricky part of this process, I think, is finding that t star, finding the cutoffs that you need. You need to adjust those based on the confidence level and how many degrees of freedom you have. Are there any questions? You guys want to like give me thumbs up or thumbs down out there? Something. Okay, thank you. 2 thumbs up. Awesome. Thanks. Okay, and there is thank you, John. There is a built-in function in R that can do this as well, and that's called the t.test function. If you're looking in the worksheet, the PDF version of the worksheet, it describes this command in R, which is called t.test. So here is R can built in do all of those calculations for us that we just broke down step by step. I don't know why I'm calling this. We're not outputting this anywhere. So the command is t.test, and the input is your sample, confidence level, and then on after this command, we're going to put a $sign and then conf, because we're also going to be able to use this to do a hypothesis test for us. So by including this on the end, this tells R to not do a hypothesis test, but to tell me what cutoffs would be for a 95% confidence interval. So in this case, you would change the name of sample to whatever your sample data is. Mine is actually in something that I called sample. And here our confidence level in this case was 99. So I'm going to put that in, not as a percentage, but as a decimal. So I'm going to enter that as 0.99. And this is a slightly more complicated command because it reads in this large data set and does all these calculations. So it might take a second to do it. It didn't even take a second to do it. It took less than a second. And we get exactly up to some slight rounding differences, right? Or not even, we're getting exactly the same answers that we got by hand. So we certainly could have just done this all in one step and we would have gotten this value over here. But I do think it's important to be able to go through those calculations on your own as well. Any questions? Okay. Let's see. So here you're over here. So if we want to interpret this, remember last time we did spend lots of the time thinking about correctly and incorrect ways of interpreting these, which is really important. So you know, the two things that we focused on, first of all, is when we have this uncertainty, we're not guaranteed this is going to work, so we should attach the uncertainty to the interval, which is based on our sample, our randomness of sampling, and not on the population parameter. So we're going to say there's a 99% chance that the interval, and I'll just resave that. So that's going to give me the lower cutoff was grams. So that's one way we could interpret what that means. Any questions? I can run this to see what happens. So here, this got output to HTML. Great. You can see when we do those inline commands, it actually does output the values that we stored up here previously. That's good. That's pretty narrow range of values considering how large we're dealing with, like 3,000 some odd grams. So, you know, the upper and lower cutoffs are only differing by about 80 grams. So that's a pretty good narrow window of that we can use as an estimate. Okay. Any questions? Okay. So then let's take a look at what we do when we have a difference of two means. And so this is what you guys watched a bit about for the reading quiz for today. So when we were doing confidence intervals before, let me just say, so we've got a confidence interval for a single mean that we just did. So the cutoffs would look like that if we were doing a single mean. If we were doing a confidence interval, I don't have any on this worksheet that, that deal with matched pairs. But if we had a matched pair sample, right, that means you have a whole bunch of pairs of values, and for each of those pairs, you calculate a difference. We have difference 1, difference 2, all the way down the difference sub n. So if you were doing a confidence interval for matched pairs, you just create a confidence interval for the differences of each of the pairs.
Close that door.
I don't know why I had a 2 over here. This was all wrong, sorry. This one is the standard error is s divided by the square root of n. So point being here is if we have a matched pair problem, we calculate the differences in each of the pairs, and then we just do a regular confidence interval on the differences. So I would calculate the mean of these differences. That's what goes over here. I would calculate the standard deviation of those differences. That's what goes over there. And the n and the t alpha over 2, we would do the same. I'm not sure if I don't think I asked any matched pairs on homework. They're none on this worksheet, but it would be done the same way as if we had just a single mean. For differences in two means, we kind of went through on that video, went through pretty much central limit theorem type of stuff for differences in two means. So the first thing is we would expect the differences in the sample means to be equal to the difference in the population means. And then secondly, with variances, when we pull out constants, we square them. So the variance here, when we simplify it, came out to sigma 1 squared over n1 plus sigma 2 squared over n2. So we don't really change how we're constructing these confidence intervals. We have a point estimate, which is going to be the difference of our sample means. We have a standard error, which we now use this formula for, where S1 and S2 are the standard deviations of each individual sample. And then we have this T alpha over 2. And so for this T alpha over 2, we do it the same way. It's based on the confidence level and on your sample size. Okay, but now the problem is there are two samples to work with. So what do we do, right? We've been doing degrees of freedom is the sample size minus 1. So there is kind of an informal way to do it, which is you pick the smaller of your samples and you use that to calculate the degrees of freedom. So you just err on the side of caution. For whatever it's worth, there is a more accurate approximation that you can get using this formula down here. I will not ask you to calculate those by hand, so don't worry about that. If you're going to do these things by hand, we're going to just use this method over here. Or there is an option as well in R to use the t.test as well. So now you would be comparing the means from two different samples. So you would put sample 1, sample 2, confidence level, and that. Okay, any questions? So let's take a look at an example. I'm going to jump back into R to do this one. But the idea here is we're looking at students who were randomly assigned to two different groups. One, students took notes by hand, and the other students typed notes on a laptop. And we can see how many students were in each of these groups. And then they took an assessment, and they calculated the average of how students did on the assessment based on how they took notes. So for the students, the 38 students that took them by hand, their average was 25.6. For those that took notes on laptop, their average was less than that. It was 18.3. And then we've got the sample standard deviations for each of these calculated. So in this case, we can't use the t-test option. Okay, since we don't have the raw data. Right, I don't have this data set of here is every single individual student and here's how they did. So that t-test works when we have the raw data. When we don't have the raw data, then we're going to need to use the formula that we had up before. Okay, which would be I calculate the difference in my sample means. And then we add and subtract the margin of error onto each of those. So in this case, we have to use that formula, right? We don't have the raw data, so the t-test won't even work for us. And our degrees of freedom in this case would be, we take the minimum of the samples, which is that 38. So we're going to use a t-distribution, 37 degrees of freedom. And then we are using a 95% confidence interval. So we want to include the 95% in the middle and the 0.025 in the left tail. So altogether, the total area to the left is equal to 0.975. Oops. Okay, so those are the 2 bits of information we're going to need in order to find out what T alpha over 2 is. Any questions? Okay, well then I will use R to do these. Yeah, okay, so here we are, this last question on this worksheet. So if you want to go ahead and give this a shot, go for it. maybe that's what I'll ask you to do. Go ahead and try and construct this 95% confidence interval. So try to do it on your own, and I'll work on it, and then we can compare how we did things. I think these are one of these things where you'll get a lot more out of today if you're actually trying to do it yourself and not just waiting to see how it's done. And if you have any questions as you're working along, feel free to chat either to everybody or to me or Yua, and we can certainly give you some feedback in the chat if you have some questions. Okay, so let's compare our answers on this one. So here's the R code that I used for that. You could probably do this in a single line, but I broke down the calculations, same exact calculations as we did up here. The only difference is we have a different standard error calculation. Otherwise, just repeating the exact same steps from the previous example. Our point estimate now would be the difference of the two means. Standard error is s squared over n plus s2 squared over n to t star. We talked about on the PDF why we use 0.975 and why we use 38.1. And then we get the margin of error by taking the product of those, and that gives us confidence interval here. So on to B then. Unless there are any questions, I'm not hearing or seeing anything in the chat. Then if we want to interpret these, we could say something like, you know, there's a 95% chance the interval from lower to upper contains the difference in mean exam scores between the two groups of students. And the question here is, well, do you think there is a difference in these two groups based on the values that we have up here? So do you believe there's a difference in the exam scores of the two groups based on this?
Is it just because since the lower and upper, since there is a value, like since the value no matter what would be different than 0, then yes, there is a difference?
That's exactly right. Yeah, thank you, Stephanie. That's exactly right. Here we're really thinking about, is 0 in this interval? If 0 is in the confidence interval, then that's a plausible value for the difference, meaning that it is possible that there is no difference between those two. When we get a confidence interval for a difference of two things that is always positive or only negative, in other words, that doesn't have 0 in it, then we have evidence that there is indeed a difference between these two groups. So in this case, we would say yes.
And that's because there's no 0 in the interval.
That's right. Okay. Great. So then Welch's approximation, if you were to actually go through that horrible looking formula and calculate that, comes out to more accurately the sampling distribution. Rather than use 37 degrees of freedom, it's more like 72 degrees of freedom. And so I just want to kind of highlight, well, like, what would be the difference there? The only thing that's going to be different, right, would be the t star value. It's not going to affect the difference in means. It's not going to affect the standard error. So the only thing that we would need to do is adjust the t star value that we're using. I'll call this t star 2. It says, okay, we should not be using 37. We should be using 72 degrees of freedom. But otherwise, Everything else is going to be the same. So I don't need to change the standard error, and I don't need to change the difference in means, but I do need to adjust my margin of error. That's it, right? So the only difference here is changing that 37 to a 72 and then updating the margin of error based on that. And okay, there you can see the difference, which is why I'm advocating that we don't need to worry about being so detailed about Welch's formula using 37, right? Gave us essentially the same confidence interval. We're off by like, really small values here. So if you want to be more precise, we can use Welch's approximation. If we're comfortable just kind of error on the side of caution, then it's totally fine to just take the smaller of the samples and subtract 1. And at the end of the day, we get almost the same approximation. Okay. So that's all I wanted to talk about for mean. So I want to use the rest of the time to talk about what we do with proportions now. But any questions about means before we take a look at the next worksheet? Okay. So this is worksheet 15 now, but the R markdown file is the same for both of these. And let's see, here we are. Okay, and so here it's vaccination season here in Denver, opened up to the general public. So I thought it might be interesting just to take a look at data here. This was a recent poll from a couple of weeks ago as far as how likely people in the US were to get vaccinated. There is this vaccine hesitancy. So in order to reach herd immunity, right, they say we need about 70 to 85% of the population to either be vaccinated or have natural immunity to it. So if we kind of think about I'm just going to think about like all adults grouped together at first, we can see that in here, there's about 30% of the population says they're not going to get vaccinated at this point, which is kind of dangerous here because we can't vaccinate any kids yet. So if 70% of the adults are vaccinated and none of the kids are vaccinated, we might not get there. And then we can take a look at the breakdown by political party just to see how that plays a factor. And down here, if I zoom in really close, right, most people ignore this stuff. This is the awesome stuff where you can see how many people were in this survey and what the margin of error is, right? So they've calculated the standard error and then multiplied that by some factor to account for this. So when we get the margin of error here, you can see how statistics is done in practice. It's kind of sloppy because they don't tell us for what confidence level. So you should almost always assume, unless it's stated otherwise, that this margin of error would be for a 95% confidence level. So we'll see if we get something consistent with that. So we don't need to kind of develop a whole new method here. We just need to tweak the formula a little bit. So now we're going to use the central limit theorem for a proportion. So remember, when we were trying to describe the distribution of sample proportions, we said that the sampling distribution is going to be centered at the population proportion, and the standard error we use the binomial distribution to get a calculation for the standard error. So we can kind of just use the same old trick that when we knew what the population variance was, we said this was how we can construct it for a mean. And we're just going to do the same thing, except now we're not approximating a mean, we're approximating a proportion. And our initial guess is going to be the sample proportion. Okay, we're going to use a normal distribution since central limit theorem tells us that this is going to be normal. So that's why we're going to use z alpha over 2. And then in place of p in the formula for the standard error, we're going to plug in our estimate for it, which is going to be p hat. So here we've got our point estimate comes from the sample. Our estimate for the standard error comes from that. And then we use a normal distribution to adjust for the confidence level. So kind of answering this question, you know, we could algebraically move this stuff around and solve that for p, and we would get the same interval that we have below. So for 95% confidence interval, those values are going to be 1.96. When we adjust the confidence level, then we need to adjust those as well. So if we were to try and construct a 95% confidence interval for the proportion of adults that are not going to get vaccinated in the US, we can kind of, let's do this by hand first. And let's kind of use the fact here that in our sample, I'm going to just consider the people in the sample that actually were registered to vote, since we're going to tie this into political party in a second. So out of that sample that they originally polled, not everybody was registered to vote. So 1,082 people were registered to vote. And out of that group, that previous chart had 29% of them said they did not plan to get vaccinated. So our proportion, our sample proportion is 0.29. That has been calculated for us. So that calculation for the standard error, right, that would be the square root of 0.29 times 1 minus 0.29 over 1,082. And if I wanted to find the z alpha over 2, now we use normal distribution again. So we go back to Q norm. Okay, or you can recall for 95%, that's going to give us 1.96. And then we can plug in our values to get the corresponding cutoffs for the interval. But I will go back into that R markdown file to do the calculations here. Good. So we got the same info here. That's good. So we've got 1082. I'm just going to call my sample p hat. That's 0.29. And you just want to be sure you're careful about how you enter these formulas, using parentheses carefully. So my standard error is going to be the square root of p hat. I can, now that I saved it, times 1 minus p hat, all divided by 1082. Maybe I'll save that as n. And then we've got our z star value, which we use the standard normal distribution for. So that's where the 0 and the 1 come from. Now we've got the margin of error is standard error times z star. Okay. So this should do the trick, right? Calculate my sample mean, calculate standard error, and then calculate my cutoffs. So this is telling us that there's a 95% chance that between about 32% of the US population is not going to get vaccinated. At least at this point, they're not planning to get vaccinated. Any questions about that?
So the confidence interval is just based off of p hat now instead of x bar. And then the standard error changes as well in the confidence interval.
Yep.
Okay.
Yeah, so we're using central limit theorem now for a proportion instead of a mean. Yeah. And we're going to use p hat in the formula for the standard error since we don't know what p is. So what we just calculated, that's what's called the Wald confidence interval. So yeah, I mean, this is nice. We could do it by hand pretty quickly. The downside here is that when we use p hat in place of p, I'll just say p hat is an unbiased estimator. That's good. But it's not that efficient. So it has a bigger variance. So the confidence interval down here, which is called the Agresti-Coull confidence interval, rather than use p hat as the point estimate, they use this thing called p tilde. And let me just explain what this is. So p tilde is going to be, we're going to assume that there are 4 more observations in our sample. So we're going to consider our sample size now to be n plus 4, and we call that n tilde. And out of those 4 that we added, we're going to assume 2 are successes, whatever that might mean. Okay, for us, in this context, success means a person who is not going to get vaccinated. That's a failure in my mind. And now, so that's going to be our new number of successes is going to be the original number of successes plus 2. And I'll just say, you know, why would we use this instead of the original one? I'll just say that this is a biased estimator. But it's more efficient. We kind of mentioned these properties a little bit when we were talking about estimators. So it's biased. It's not very biased. As n goes to infinity, the bias is actually getting closer to 0. And what's really nice is that the variance of this estimate is smaller than in the previous case. And this is what's called the Agresti-Coull confidence interval for proportion. So we basically do the same exact thing that we had up here. We just replace each of those p hats with p tilde. And each of those n's with n tilde. The z alpha over 2, that is not going to change. Okay, that's going to be the same in both of these cases. So let me come over into R and calculate this using R. I just do that. I just unshared and reshared the same thing. Here we go. I want to share RStudio. So for the Agresti-Coull, I can almost use all of the same stuff that we have over here. So I'm going to just make a note here. The original sample had, right, we were told originally what proportion of people said they weren't. If we're going to use this method, we need to know how many people out of the 1,082. So that 29% that we had, that came from 314 out of 1,082. So my p tilde is therefore going to be, I'm going to add 2 more people to my I'm not going to get vaccinated. And I'm going to add, right, 4 people to the sample. So here we're including 4 more people, assuming 2 of them said they weren't going to get vaccinated. I'm going to have a new n value, which I'll call n tilde. I have a new standard error that I'll call standard error dot tilde. And the only difference is this uses tilde for the proportion as well as the sample size. Okay, so I adjusted both of those things now. the Z star value that doesn't get affected by this, but now the margin of error will, because we have adjusted the standard error. So this is going to give me upper and lower estimates for Agresti-Coull. That's where the AAC that I used came from. So now we use our P tilde plus margin of error tilde. And that's going to give me my updated confidence interval. Okay, so really, again, the only thing I've changed is what I'm using as my estimator. Instead of using the sample proportion, I'm going to use this adjusted sample proportion where we've included some additional observations. Any questions? And here's what I got, and here's what we got from the previous one. And again, you know, very little difference in the accuracy here, but it does change things slightly. Any questions?
Is it usually that small of a change, like a 0.1%?
That's a good question. It depends on how large your sample is. So if you have a smaller sample, that difference is going to be more pronounced. We had a sample of like 1,082 people, so we didn't notice as much of a difference. If we had 82 people, then I think we would see more of a difference in that.
Okay.
Okay. Then one last method of that I want to share on my iPad of doing this is what's called the score confidence interval. Yeah, and so the idea here is like if you in a standard normal distribution, right? We know that that is 0.95. And so if we're working with the distribution of p hat, then central limit theorem told us, okay, here's how those proportions, sample proportions, are going to be distributed. So if I wanted to normalize this distribution, I have some sample. I could first calculate, you know, how far away is it from the center, and then divide that by the standard deviation. And so the alternate way of doing this is to think about right. We have this equation, and the things that I've highlighted in yellow are the things that are unknown. And so I could take this equation which is like this one over here. I pick a sample, so I know what p hat is, and I know what n is, And then I've got some nasty looking equation that I can solve for P. Just say that. So I can think about this as an algebraic equation where the only unknown is P. And when we solve that equation, right, these are the formulas that we get. It involves quadratic formula, and it's pretty messy. But this is a more accurate way of doing it than the previous two, because in this case, we're not plugging in any estimates for P. We're plugging in information that we've observed, and then we're solving for what would be the cutoff for P upper and lower. That's going to give us 95% in the middle. So this is what's called score confidence interval. This was done by mathematician Wilson. So sometimes it's called Wilson's score confidence interval. This is like from the 20s. This is a pretty old school 1920s. I now need to qualify that we've hit 2020s. This is like 100 years old. That's how old school this is. And it's actually more accurate than the previous two methods that we've talked about. And so the nice thing is this is the formula that R does. Okay, so in other words, we don't need to enter these things in ourselves, but we can use this proportion test feature in R to calculate it for us. So if I wanted to do this in R, what we need to know, X in this formula is denoting the number of successes in our sample. Okay, which again, for us, that was like 314 people said they weren't going to get vaccinated. And N would be our sample size. And then we can adjust the confidence level accordingly. So in this case, if I wanted to calculate this using R, using this prop test, I would say prop test, first thing I do is input the number of successes. 314 people in my sample said they're not going to get vaccinated. Out of 1,082 people in the sample, and then put my $ confidence level. And this is going to calculate what's called the score confidence interval. So just to wrap things up today, just to compare this to the others, if you actually do want to play around with that score confidence formula, I did enter it in here to some extent, but I'm just going to skip using that formula because the prop test is going to do it for us. And so here we would say the 314, 1,082, my confidence level, 0.95, and don't do a test, do a confidence interval. And here you can see, you can compare these to what we had up top. There is some slight difference again, but very, very minuscule, I think, overall. So they give us slightly different intervals, but right, we're not getting drastically different confidence intervals. Okay, so there's one last example that we didn't quite get to on this worksheet. So yeah, we can pick up thinking about this next time, but I'll just say the short answer is we could just modify this prop test. This won't take us too long to finish up. So then the plan for next time is to kind of revisit some more classical methods of doing hypothesis tests. So we kind of talked about bootstrapping, and then talked about more traditional confidence intervals. We've talked about permutation tests. Now we'll talk about kind of more classical ways that people do hypothesis tests as well. So that'll be the last bit of material for the semester. So that puts us in chapter 8. That's the last chapter we're gonna talk about. So starting on Monday and then the 2 weeks after spring break, we'll just be focusing on working with hypothesis tests. So your homework that's due this week is all about estimators and confidence intervals. So you should be good to go on those. But if you do have any questions, feel free to stop by office hours for Yuval and myself. We're happy to help you with those. Otherwise, we'll see you on Wednesday. Have a nice Tuesday, and I'll catch you guys on Wednesday.